we will try our level best to get some question after your second lecture.
Yes.
Thank you so much.
Okay, good. Let me let me just spend maybe 5 minutes to finish this part. Why? Because this is a collective problem. Although in machine learning and AI, few people are doing this. It's a collective problem in statistics, right? But at least we should have a clear picture. So those assumptions, you can see the first one, ignorability. Basically, with the ignorability, you can just convert the average treatment effect involving this guy, potential outcome, to conditional distributions. Okay? Ignorability says the following thing. Treatment and the mechanism to generate other potential outcomes are independent. Okay? So there are nowhere for them to be related. Right here, you have treatment, you have mechanism to assign treatment, you have the mechanism to generate a potential outcome. They are not related. This is ignorability. And if you have ignorability, you can directly go from ATE, average treatment effect, to conditional distributions, okay, by following the properties, ignorability and consistency. And even if you don't have that, you have a conditional ignorability, conditional X, you have this conditional independent relationship, then you can do something similar. Here, X like age, right? If age is given, then we can still identify the treatment effect of T on Y. Here, there's a difference. We first identify the conditional ATE cake, conditional average treatment effect by conditional X. And then after that, we remove S. We take another expectation to remove X to find the average treatment effect. We take expectation of X. Okay? So this is ignorability in the potential outcome framework. Later, you can see this corresponds to some other graphical criteria proposed by Pro and Peter Spertis. Okay, so now comes one difficulty. Let me just direct you that positivity, this is trivial. No, interference, this is also trivial. This says your potential outcome shouldn't depend on whether others receive treatments. It only depends on your whether you are treated, right? So basically, this is a no interference assumption. Normally, it's true, but you can come up with counterexamples. For instance, job training for too many people may flood the market with qualified job applicants. As a consequence, this guy, the outcome for you will also depend on whether others are educated, right? So, and consistency is also trivial. And then you put them together, you can just find a causal effect. So now let me just explain one thing. In order to find the average treatment effect, we have to go from a conditional treatment effect, average treatment effect, to the average one by conditional X, right? By taking expectation over X. Now the problem is, in this case, if you consider two groups, treatment group and control group, the X distribution is different. Why? Because here we don't have ignorability. Right here, you can see across two different values of T, X distribution is the same. In this case, if you have ignorability. If you don't have that, even if you have a conditional ignorability, you can see that across two values of T, X distribution will be different. How can you use the same distribution of X for expectation, right? When you take the expectation, that's a problem. So that's a classical problem statisticians have been trying to deal with. There are basically three ways to solve the problem. The first one is to use regression adjustment. I do regression model right here. If I have a regression model for this guy with a T equal to 1 and this guy for T equal to 0, since I have two regression models, I can just use the same distribution of X as input. I can calculate the difference, right? So this is because I have a model, parametric model. I can always use the same X distribution. Or this is regression adjustment. And the second one is to do matching. The first way is to directly match the original X data points. Right here, I have treatment, I have right here control and treatment. I just try to see whether they are very close by. If they are very close by, I say they have the same value. That's it. So I just try to match the distribution of X across two groups. But this is very difficult, especially if you have a high dimensional data, it's almost impossible. Then we can use the propensity score matching. That's it. And there's only one difference. The propensity score is a random variable defined this way. Propensity score is the conditional probability of treatment equal to 1 given X. Now, no matter how many dimensions you have for X, the covariance, This is a single random variable, univariate random variable. And then you can show that if you have the propensity score, instead of matching the original covariance, you can just use the propensity score for matching. If we have the same propensity score across groups, we can be matched. Okay? And then we just use the propensity score for matching. It's very simple because it's one-dimensional. That's it. If you care about theory, talk to me afterwards. And then here you can see the graphical criteria. This is called the backdoor criterion. So if the backdoor criterion is satisfied by Z relative to XY, then we can identify the treatment effect of X on Y by adjusting Z. Yes. You mean direction right here?
Yeah.
Yes. In that case, if that's the case, then first of all, generally speaking, we do not consider cycles. Yeah. And second of all, even in that case, you can still do something. You can do intervention. Yeah, you can still, actually the result would be the same. Why? Even if you don't, very good. If you have temporal data, then you don't have cycle because you just always, exactly. If you unroll the data, you don't have cycle. There's no problem. But even if you don't have that kind of data, you have cycle. But basically here, we only make use of the dependence pattern. We just try to, you can see in all the derivations, we just try to make use of dependence pattern. We know T depends on T causes Y. And at the same time, if you have X here, give me 1 second, then the equation will be different. It's still doable in that case. And right here, we assume that X covariance are just potential causes of the target. Okay, good. So here, the message is as follows. Instead of using ignorability or conditional ignorability, we can use a graph condition. Okay, developed by Peter Spertis, Yuda Pro, from CMU and UCLA, respectively. So basically, if Z, say H, satisfies the backdoor criterion relative to XY, then the causal effect is identifiable. And right here, we don't have time to talk about this kind of example, but let me just go. You can see the following thing. This is the backdoor criterion, and this is the conditional ignorability condition. They are equivalent. Under very weak assumptions, the conditional ignorability condition and the backdoor criterion are equivalent. So basically, they try to use different perspectives to study the same thing. They try to see whether causal effect is identifiable by using two different notations. Okay, that's it. And similarly, we can also have a front door criterion, as you can see from here. Although we have latent confounders for XY, if you observe Z, which is in the front door relative to XY, then you can still identify the causal effect of XY, although you have latent variable here. Okay, this is called the front door criterion. And you can see it's also relevant to, or it's related to some other ignorability conditions. Okay, the message is as follows. The potential outcome framework and the graphical conditions are closely related. They just try to see whether causal effect is identifiable by making use of different languages. That's it. The last thing right here is about the counterfactual. For this one, let me give one example. Here, we have attendance grade. Suppose attendance is the cause of grade, right? Attendance is the cause of final grade. Suppose that's the case. Then we have so many, you can see we have function. This is the function called model, stratification model. Final grade is the log transformation of attendance plus noise, unobserved variable plus 3. Suppose that's the case. Now come the question. Suppose this is me. For me, I have this value of X and this value of Y. My attendance is low and my final grade is very poor, as you can see from here. Now, suppose you have a way to force me to change the attendance to X prime. Where is my Y value? So, right, if you just use machine learning, you say, oh, I can use expectation, right? But from a counterfactual perspective, that's not true. Why? Because intuitively, if you observe this X and Y value from me, compared to other students with the same X value, my final grade is very low. Is that right? This means maybe I don't pay attention, or I'm dumb in some way, right? So this information will not be different because of this intervention. I'm still the same person. This is what we mean by discovering the hidden features. We can discover the hidden feature of this particular student and make use of it. So here, basically the value will be here because my relative location relative to other students will be the same. Even if you change X, my inner feature, like how I pay attention, will still be the same because that part is not changed by this intervention. Okay, then this is my Y value. Okay, how can we derive this result? So first of all, you can see this standard definition. We talk about a particular unit, the me, right? A particular unit, and we try to see what would happen to Y if X has been different. And then here you can see how we can answer the question. We just use 3 steps, standard steps. First, we find the information of the unobserved variables, U, noise terms. And then we make use of intervention. And then we just use this information of the hidden variable together with the intervention to predict Y. And here, basically, we first find the value of the unobserved variable or noise from my XY value. And then I just use this noise value together with the new value of X to predict Y. That's it. This is a standard way to do counterfactual reasoning. Okay? We can see it's different from traditional prediction. Why? Because you try to, given a causal model, we know what you mean by noise. We can try to infer the information of noise and make use of it. Because noise is my inner feature, right? My inner feature will not be different because of the intervention. Okay, cool. This part is done. So basically you can see classical problem, what we mean by causality, intervention, how to identify causal effects, why it's called the potential outcome framework, and why counterfactual reasoning is different from traditional machine learning or prediction in machine learning. Okay, now let's go further. Let's try to discover causality from data, right? And this part of the work was basically done at CMU by my colleagues and me. So let me start with the story right here. Questions? Okay, so you can see identifying causes is always important. It's so important, especially if you identify hidden causes, the world can become totally different. This is the true story. So until the mid-19th century, puerperal fever was very popular. A lot of women failed to survive because of this after giving birth, right? So what caused that? So in Vienna, there were two clinics with almost the same techniques, but very different mortality rates right there. So you want to identify causes. So here comes the hero, Ignaz Semmelweis. So he examined all possible factors and then finally concluded that the cause should be some unseen, unknown, cadaverous material on human hands. Basically, on doctors or nurses' hands. And given this understanding, he proposed intervention, which is washing hands properly. All of a sudden, the world became very different, right? So now you can see, indeed, we can identify causes, even if the causes are originally hidden, because at that time, they couldn't directly observe virus, right? As a consequence, it's a conjecture, it's a hypothesis. But still, by making use of your understanding of the hypothesis, you can try to come up with the interventions. You can make a difference. Specifically, I don't know whether we can play this video. Okay, so later, maybe you can play this video. Oh, YouTube video cannot be played, right? Okay, so I will skip this video. Basically, you can see how we can go to the whole universe or very small things. And then each time, a lot of things are just hidden. Because what we can measure is basically inherently limited by what we believe, right? And in this case, scientific discovery basically is achieved by making use of what we can measure and trying to discover new hidden things, right? You can discover new hidden entities like gravitational wave or hidden laws like F equals ma. Each time when you discover new hidden things as causes or laws, then you can go to next step, right? You humans can become more resourceful because we can make use of more information or more resources. Okay, you saw this example before. Now let's try to see how we can discover causality. And we know, yes, we have to discover causality. Otherwise, it makes no sense. Okay, what's causal discovery? Causal discovery is the task of estimating the underlying causal structure from observational data. So you are given data. You try to identify the causal structure. And in some situations, the causal structure can contain hidden variables. And specifically, in machine learning, in recent years, people have been doing causal representation learning. Causal representation learning basically is causal discovery, but for some reason, it mainly focuses on high-level hidden variables. For instance, you may want to discover concepts from image pixels, right? Image pixels, nearby pixels are dependent, but there are no direct causal inference in between. They are dependent because of the high-level concepts, right? So in causal representation learning, we mainly focus on how to discover the high-level hidden variables from raw pixels, like raw data at a very low level. Tomorrow, you are going to see how we can do causal representation learning from ID data, temporal data, and multi-distributions. Okay, and you can see how we can really discover hidden variables. For now, let's mainly focus on causal discovery. Okay, we try to find a causal structure or causal representation with identifiability guarantees. Once again, in causality, we try to recover truth. That's why identifiability is always important. Okay? Without that, you can discover some model, but the model may be different from the truth. It's useless. Now, first question comes. Do you think it's possible to discover causality from data? Some people say no, right? Because, see, you cannot even define causality just by making use of statistical information. How can you discover causality from data, observational data? Do you think so? Now comes the first example. So actually, this is a question, the homework assignment for my son when he was 4 years old. So you can see right here in the kindergarten, they were asked to determine order, the temporal order. We know temporal order is consistent with the causal order, right? So now, can you determine the temporal order? Which one is the first? Which one is the second, and so on? Can you? The last one is the first, right? Wonderful. The teacher will be very happy. So the first, and then second, right? Second, third, fourth, fifth, right? Okay, wonderful. Do you agree? Do you think it might be wrong? Can be wrong. Why? Yes, or the kid may just remove the penny, right? Remove the penny from the fence. But that's less likely. Why? Because you can see right here, yes, the kid was happy, and at the end, right here, well, the kid was sweating, and right here, you can see the color is also green, at the beginning is yellow. Right? So it seems that the kid was using something from right here to change the color. So this story is the simplest. You can come up with another story. Yes, at the very beginning, the kid was running. That's why the kid was sweating. At the beginning, color, yes, you can see the color is green. And after the kid finishes the work, she also washes everything. You can see it's possible, but not plausible, right? Why? Because it's a very complex story. There's a lot of coincidence, right? So in other words, if you prefer a simple story, then you will say this is the first one, this is the second one. The same thing happens to causal discovery. You have to make assumptions. And if, fortunately, a lot of assumptions are testable. You can try to see whether the assumption holds true. If the assumption holds true, and you have this result, then you are pretty sure about it, right? Okay, so good. Now we know it's possible, but we need to make assumptions. Okay, all methods for causal discovery basically rely on one property of a causal system, known as modularity, or exogeneity in economics, or independent causal mechanisms formulated in machine learning. Basically, it's the same thing. You say the same thing. So here we have variables. Variables can be dependent. We have rain, wet ground, slippery. Variables are dependent. However, we can decompose the whole system into causal modules or causal processes. The first one generates rain. The second one generates wet ground from rain. The third one generates slippery from wet ground. Although variables are dependent, those modules or processes are irrelevant to each other. They are separate. They don't share information. They don't share parameters, anything. This is what we mean by modularity. We have separate or independent modules to generate different things. They can share variables, but they don't share any other information. They don't share parameters. In other words, how you make it rain is totally irrelevant from the process from rain to wet ground, because they happen in different places, right? They are not relevant. So this is known as modularity. All causal discovery methods can be derived from this perspective. So first of all, given modularity, we can see rain and slippery would be conditionally independent given X. We can see conditional independent relations among the variables. Later, you can see classical methods for causal discovery rely on conditional independent relations. Second, I have wet ground. I have other omitted factors in the process to generate slippery, right? If they don't share other common causes, then the way to generate wet ground and the way to generate other omitted factors or noise would be irrelevant. In other words, the noise term would be independent from the cause X. This is known as independent noise condition. And furthermore, suppose now you just travel in the world, and then you can see the joint probability distribution can change, right? Suppose now only as the probability of rain can change. Now, because this change and because of propagation, all the distribution can be different across different locations, right? The joint distribution can be different. However, with the correct causal representation, you can see all changes can be attributed to the change only in the probability of rain. This part is still invariant. This part is still invariant, right? That's the only change. But if you use the wrong causal model or alternative causal model, you have to incorporate more changes. And those changes will be dependent. So this is what I mean by minimal and independent changes in the causal model. Okay? If you have non-stationary environments, you can make use of this property to discover causality. Later, tomorrow, we are going to see a more broader, much broader setting called representation learning. We can allow a lot of latent variables and so on. And then we can have the three axes of the problem, including what kind of data you have, whether you assume it's linear or some other parametric models, or whether you allow a lot of latent variables. But for today, for now, let's focus on classical methods for causal discovery. Okay? So, maybe I have to skip this part because let me see. Okay, I will skip the first part, the probability theory. Why? Because in this part, I just want to explain one thing. I will just give a message. And then we will have a look at classical constraint-based method for causal discovery, including PC, Peter Clark, and FCI, fast causal inference. And then let's have a very quick look at the score-based method for causal discovery, known as GES, greedy equivalence search. And then let's look at more modern methods, functional causal model-based method. If you are willing to make some assumptions, all of a sudden you can discover the whole causal structure from data. Okay, so independence is so important. Independence allows us to divide and conquer, and independence allows us to discover causality. Why? Because basically, if things are independent, we believe for some reason there are no causal inference in between, and then we can use this to explain why things are dependent. In other words, we do the following thing. No causation in because they are independent, causation out. We can try to see why things are dependent. Okay, so independence is very important. we say they are independent if the joint CDF, cumulative distribution function, or PDF can be factorized this way, or if the condition one is the same as marginal. Okay, because the second guide does not contain any information about the first guide. Let's see. Correlation. Are they uncorrelated? Now, very quickly, according to the scatter plot, do you think they are uncorrelated? By uncorrelated, I mean the correlation or covariance is 0, right? And the covariance is nothing but the expectation of the product after you center the variables, right? So do you think they are uncorrelated right here? They are the product of the two variables after center them, right, would be 0. I mean, the expectation of the product would be 0, right? So they are uncorrelated. Okay, are they uncorrelated? It's the same, right? Positive, negative. The product cancelled out. So again, they are uncorrelated. The same thing happened here. Positive, negative, positive, negative. So expectation of the product will be 0. Okay, across all three situations, they are uncorrelated. Are they independent? Yes, right? Because the conditional distribution of one guy given the other is always the same. In this case, are they independent? No, right? Conditional distribution of this variable given the value of this guy will change a lot. Even, right, you can see the range change a lot. Clearly they are dependent. Clearly they are dependent because X even determines Y, right? So now you can see there's a big difference between zero correlation or uncorrelatedness and independence. Okay, let's go further. If they're independent, they are uncorrelated, right? You can show that. But if they are uncorrelated, it's not necessary for them to be independent. In one case, they are equivalent. In the joint Gaussian case, if they follow a joint Gaussian distribution or multivariate Gaussian distribution, then independence and zero correlation are equivalent. Okay. So this is the Gaussian distribution. You can see why. Because in the Gaussian case, it's specified by the mean, vector, and the covariance matrix. If the covariance is diagonal, then you can always factorize the joint probability density as a margin product of marginal ones. Okay, good. However, generally speaking, independence and zero correlation are very different. Later, we are going to make use of this observation to discover causal asymmetry. We use the Gaussian distribution for multiple reasons. It's very simple and so on. Okay. However, this is central limit theorem. However, there's another theorem which was overlooked. It's called the Kramer decomposition theorem. This theorem is very interesting. It says the following thing. If the sum of a finite number of independent variables is Gaussian, then each of them is Gaussian. What does that mean? It means that if I receive any contribution from a non-Gaussian guy, then I'm not Gaussian. Okay? So this means in this world, actually distribution should be non-Gaussian instead of Gaussian. Because we receive a kind of the contribution from a finite number of variables, right? Or independent factors. Then if any of them is non-Gaussian, I will be non-Gaussian. So we can make use of non-Gaussian distribution to discover causality later. Okay. If you are really interested, this is chapter 7 of the book, Probability Theory, Logical Science. Wonderful book. So it gives the origin of Gaussian distribution. You can derive the density of Gaussian distribution by making use of different assumptions, and each of them can give you the unique property of the Gaussian distribution. Okay? Now, let's look at the constraint-based method for causal discovery. So first, let's see what we mean by causal sufficiency. Here, we have a system, causal system involving X, Y, Z. If you only measure X, Y, then we say it's not causally sufficient because the common cause is not contained in the set of variables. And if all three, Z, X, Y, are given, then we say the system is causally sufficient because the common cause of any two variables is also in the set of variables. Okay? In other words, if there are no hidden or latent common cause, then the system is causally sufficient. But if you have hidden common causes, then it's causally insufficient. This can create actual complication. because you have common cause that are not given. Okay? This is called a V structure. So we have two causes that are not related and one child right here. This is called a V structure. This is very important because if you have three variables with the same skeleton, then we can determine this structure. Any alternative one, including this one or this one, with this one, the common cause and so on, will have different independence and condition independent relations. Okay, this is called a V structure. Later you can see how we can discover this structure. They are independent, given something does not contain that thing does not contain this guy, and they are causes of this guy. This is called a V structure, as you can see from the shape. Okay, this is V structure. Now, let's try to solve the problem. So we know Markov condition. What's Markov condition? Markov condition says if they are deseparated, then they are condition independent. Right? This is global Markov condition. Okay, this is Markov condition. But now we try to say something about the graph by making use of data or independent relation in the data. What can we do? We have to go from the right-hand side to the left-hand side. How? One way is to make use of the counterpositive, right? Then the counterpositive would be if they are dependent. If they are dependent, then they are not separated. Then you can always find a trivial solution for any data. You can find a fully connected graph. Then Markov condition always holds true. Because Markov condition says if they are deseparated, they are condition independent. If they are not deseparated, I have no idea. Anything can happen, right? It's always true. So now you can see we cannot use the Markov condition to discover causality. We have to make extra assumptions. What's that? So basically, this is Markov condition. From the graph, we can see independent relations. Then we make one more assumption, which is called faithfulness. Faithfulness assumption says all observed independent relations in the data are entailed by the Markov condition on the graph. Meaning that in the data, there are no extra or fake independence or conditional independent relationship. Meaning that each conditional independent relationship you can see from data is a property of the graph. Okay? Then if you make use of this faithfulness assumption, then deseparation and the conditional independent relations will be equivalent. Okay? If they are equivalent, then we can just go right from one side to the other. That's faithfulness. And the faithfulness assumption is kind of very good one. It's very intuitive. It's just like a faithfulness in relationship, right? So there's a one-to-one correspondence information. So if they are deseparated, then they are independent. If they are independent, then they are deseparated. That's faithfulness. Okay, this is faithfulness. Now we try to see how we can make use of conditional independence constraints to discover causality. We go from data. And here there are two steps. First, can we find a skeleton without direction information? Yes. And then we can determine direction. Okay? Here you can see the procedure, and then I will go talk about each of the steps. So we have data. From data, we discover independent and conditional relations. And then we start with the complete graph, where each pair of the variables is adjacent with the link in between. If they are independent, we know they are not deseparated. Then there are no link in between. They are independent, they are independent, they are independent. That's it. And then when the three are independent, now you can see this is the only possibility because this is the V structure. Because if you change any direction here, for instance, change this one, then X1 and X3 shouldn't be independent because they share information via X2. So if you observe independence between X1, 1, 3 without the condition X2, this is the only possibility. They cause X2. They are independent, they produce X2 together. Okay, this is the structure. We can find the information. And then, can you find the direction between X2 and X4? Can you further find the causal direction between X2 and X4? The answer is yes in this case. Why? Because we know X1, 2, X4 do not form a V structure. Because if this is the V structure, then X1 and X4 would be independent without the condition X2. That's not true, right? So we know it's not a bit structure. If this guy is not a bit structure, then this direction cannot go this way. It must go this way, right? It's called orientation propagation. You can propagate the direction information. Okay, now let's look at details. So first of all, we can find a skeleton by making use of only a single theorem. It says the following thing. Any two nodes x, y in the graph are adjacent with a link in between or edge in between. If and only if they are dependent condition on any subset of the remaining variables. They are always dependent. In other words, if you can make two variables conditionally independent by condition on anything, there is no link in between, right? So this, after this step, we can find the skeleton. We know whether two variables are adjacent. This is the first step. And then we do orientation propagation. We first find the bit structures, and then we do orientation propagation. That's it. So this is the idea of the PC algorithm. P stands for Peter, Swartis, C stands for Clark Glimmer. So basically the first letters of their first names. Okay. So, and finally, we represent relationship, the final output this way. If you can find the direction information, you give the direction. If you cannot determine the direction, you say, I don't know. You just use the undirected link instead, right here. Okay. Now, let me give one example. You saw this example before. I started with this one, and then I do independent test, independent, remove link, independent, remove link, and then I find the bit structure, and then I do orientation propagation. So in this case, just from data I discover independent relations, and then I can recover the true causal graph just from data over x1, 2, 3, 4. Okay. And this is the original PC algorithm. You can see basically you do independent condition method test to find the skeleton, and then find this structure, and then do orientation propagation. This is exactly what you just saw in the previous slides. Okay. This is how we can do orientation propagation. If you can find a direction here, but not here, then you can find a direction here. Why? Because I know this is not a bit structure, since I already discovered all the bit structure. Here I can get away from cycles. This guy cannot go this way, because if this guy go this way, it's a cycle. Okay. So, and then right here, we can represent the final result this way, known as a pattern. So first of all, we say two decks, direct acyclic graphs without cycle, are independent equivalent or Markov equivalent if they have the same skeleton and the same bit structures. Okay. So now, actually, we make use of all independent relationship. We know that the final result will have the same skeleton and the same bit structure because we can determine all bit structures. Then we know all results we can produce with PC will have the same, will be equivalent. And then we can just represent all the results with the pattern. Pattern is also known as CP-DAG, completed partially directed acyclic graph. I know there's a lot of terminology, right? But if you know what it means, then everything will be simple. So it's completed because you cannot go further anymore. It's partially because some links may not be directed, and it's directed acyclic graph. Okay. As you can see from here, there are three possible links, three types of possible links. No link in between, undirected link in between, direct link in between. So here, I know the direction. Here, I don't know. In some solution, x1 causes x2. In some other solution, x2 causes x1. As a consequence, I don't know the direction. I don't give the information. Okay. So consider this example produced by PC. It's a pattern. How many decks do we have in this representation? How many decks do we have? Yeah, two, right? Why? Because they can go this way or that way, right? Wonderful. Basically, there are only two. So you can see with the condition independent relations, we may not be able to discover all directional information. However, it's still very informative. You can find a skeleton, you can find a lot of directional information. Okay, I don't have time to do it, but later you can just download the tetrad or causal learn. And then you can just apply those methods to the data. You can see what I mean. I can share all the data sets later. I can share the data set with and then just play with the tools. And you can see, yes, from data, you can really discover something interesting. Okay, now come the examples. The first example in archaeology, my collaborator, Marlin Nobeck, with a very nice last name, Nobeck. Let's go forward right here. So she tried to understand the causal relation among a lot of features, because in archaeology, they try to see why we, as humans from different areas, look different, right? And they measure a lot of features and try to see why. Okay, so here you can see with the causal learn package we developed with those as a data set as the input, this is the result. This is geodistance, basically this is geographical location, and climate, diet, gender, cranial size, how big it is, and cranial shape differentiation, the shape right here, and attrition in teeth, and some other behavior. So now you can see just from data, you can really discover the underlying causal relations between those features. First of all, geodistance is the root cause. You can verify that. And then the cause is the climate, and the cause diet regarding what you can eat, and finally cause the cranial shape differentiation. And furthermore, with this causal graph, we can distinguish, we can find not only causality, furthermore, we can distinguish between direct influences and indirect influences. For instance, diet, what you eat, is a cause of cranial shape differentiation. Basically, this means what you eat can change your looks, right? However, we know this is not a direct influence. It's indirect. It takes place via attrition in teeth and some behavior. Now we know, yes, I can still eat what I want to eat. I just need to protect my teeth, right? In some way, and then I will not change my looks. Now with this causal graph, you have the freedom. You know how to make a desired difference. And the causal graph can be discovered from data. Okay, this is the first example. This is the second example. It's also very well known. It's the quality plan. So basically here we have a lot of variables, including sex of the child, intelligence quotient, and quality plans, and so on. All those things. And here you can see from data we can discover a causal graph. The last one, quality plans, is caused by parental encouragement, IQ, and so on. Okay? So this is actually the graph given by the expert. With PC, we discover almost the same thing with only one difference. What's the difference? Only one difference. Only for one link, only for one, we cannot determine the direction. Which one? This one, yes. For this one, we cannot directly rank. For this one, it's a bit structure, right? For this one, bit structure. And then we do orientation propagation and so on. So we can discover all the direction information. But for this one, we cannot determine direction. But still, just from data, you can discover almost everything about the causality. Wonderful. So this was given by domain experts. And then we forget it. We just apply the method, we do the comparison.
Basically, if the domain expert has the knowledge, if that's your difference.
Yeah. You are saying if the domain experts really have the knowledge, we don't have to do so. You're totally right. That's why, however, if you have a method, now, if you want to validate the method, you may have to collect a lot of examples where you have the ground truth. If they have to,
Is it ground truth is possible or not? How do we know what we know that the ground truth is actually the
here in this example, we rely on domain experts, right? And in the general situation, you are totally right. And this is why we do discovery, right? If you know the ground truth, you don't have to bother, right? So, however, we have to make sure the method makes sense. That's why we collect a lot of data sets with the ground truth to verify that the validity of the method.
think which will be more than grounded, and then you use the method to discover where the ground truth is not available, but we hope that because the method is there, it's probably.
You are totally right. Basically, right? So here you can see, then you can try to go further because, it's across all cases, right? With the clear knowing ground truth, I can do something very meaningful. Then, you can easily go beyond that. That's exactly the truth. Okay. Now let's try to go one step further. Previously, we assumed that there are no latent compounder, no latent common cause for two variables. Now let's drop this assumption and see what we can get. Consider the first example. I know it's a lot of information, but now you can see how we can go solve complex problems step by step. So now, suppose we have 4 variables. Previously, we already did it. So this is the result given by the previous method, PC. Now I have only one question. We know that in the universe, there could be so many variables. The question is whether it is possible at all to have a latent common cause for X3 and X4. Sorry? The question is whether it is possible at all to have a latent variable C as a common cause of X3 and X4. Latent, hidden. Yeah. Yes or no? I asked the question. So the answer should be different, right? Otherwise, no surprise. The answer should be surprising to you. Yes, no, yeah. Do you think it's possible at all? In principle, yes, right? Because there could be anything. However, given the independent patterns in this case, yeah. Yes. Now we see this set of independent relationships right here. We see this. Now we just need to go one more step. Okay. Suppose there's such a C. Do you think it's possible to observe those 3 independent relations? Right? This is how we can verify that. The answer would be no. Why? Which one? We cannot observe. Yeah. So, no, this is basically called identifiability will apply to the previous one, causal effect, right? Now, we just try to see, we observe those 3 independence and conditional independent relationships. Okay? Now, my question is, if there exists such a C variable as a common cause of X3 and X4, do you think it is possible to have this relationship? 1 and 4 are conditional independent given 3. No, because 1 and 4, if there's such a C variable, then 1 and 4 will not be deseparated by 3 because of this part. But this is the collider. So now you can see, in this case, we are completely sure that although the universe can have so many things, there are no such a variable. Furthermore, we know X3 must be a direct cause of X4. No matter how many variables you measure, that's always the case. Now this is cool because by examining only 4 variables, you are completely sure that one of them is the cause of another without any latent or hidden common cause. We are sure about it. Yes, other things can exist, right? Other things can exist. For example, you may have an effect of 3 and 4, but that guy cannot be a cause. Because if that's the case, then you can never observe this. It's not possible. Because if that's the case, if that's the truth, then in the data you cannot observe this guy. Yes, we start with data, right? So now you can see from data we know, oh, there's no such a C variable. we are completely sure that X3 is the cause of X4. So, okay, so basically you can see, even by conditional independent relations, we can still kind of provide a very strong claims about the causality, right? In practice, you can have so many examples. Right here, 1 independent from 4 giving 3, and we know 1 happened before 3, meaning that this guy cannot go this way. Then we know actually 3 must be a direct cause of 4. You can make use of this property in many examples. You can say that wet ground is the cause of slippery without a latent common cause. Okay, in this case, we are completely sure about the direct causal influence, and we know there are no latent common cause or hidden common cause. Second example, they are independent. So to make it very quick, in this case, we are completely sure. Now you can see 2 and 4 are dependent. Once again, we are completely sure that there must be. Say again?
What is the amount of the ground?
Yeah. Oh, right here. Oh, it doesn't matter. Oh, you mean in this example, right? In this example, you have a sprinkler. Yes, it can be X2. Yes, X2 can and rain can cause a wet ground, right? Doesn't matter, right? So as long as you can see, you have 1 more minute. So here's the point. If I know X3 is not the cause of X1 because of time information, and I know they are in 1 and 4 are independent giving 3, then I know for sure that X3 is a cause of X4 without a common cause, latent common cause. That's it. Why? Because I know X3 cannot be a cause of X1. I know there must be a arrowhead right here. Then if I have a C, 1 and 4 will be connected given 3. I cannot observe this guy. Okay, so now let's come to a second question, second example. So in this case, of course, you can condition a lot of things. Doesn't matter. 1, 3 independent, 1, 4 independent, 2, 3 independent. Then if you apply PC, you see here, the direction will go this way and this way at the same time. What does that mean? There's only one possibility. There must be latent common causes for X2 and X4 without direct causal influence. If there's the influence, say from 2 to 4, then 1 and 4 cannot be independent. Right? Similarly, if this guy goes this way, then 3 and 2 cannot be independent. So in this case, in contrast to the previous example, we know they are dependent, but there cannot be any causal influence in between. The dependence is caused by latent common cause. Okay? So, of course, it's another example. X1, I'm not really sick. X2, I'm in this lecture room. And 4, you are in this lecture room. 3, you are not sick. So you can see, roughly speaking, those independent relations will hold true. And then we know 2 and 4. I'm here, you are here, are dependent. But you are here not because I'm here. I'm here not because you're here. There's the common cause. What's that? We have this event organized, right? So that's why you can immediately infer that there must be common cause. Okay, this is another real example. So the electric company tried to see the source of pollution, and they measured a lot of variables, including pH, acidity, and so on, and the biomass. And they found that given pH, biomass is the condition independent from other things. And then we are completely sure that pH is the only direct cause of biomass without a direct common cause, without a latent common cause. Later, they actually did some interventions and they verified this. Okay? You can really discover true causal relations from data. I hope this is a partial answer to your question. And now comes this example. Remember this example? Chocolate consumption and Nobel laureates, right? If you collect 2 more variables right here, whether country is from Europe and meat supply, then you can see the second example holds true. Then we know actually for X2 leading in science and X4 chocolate consumption, they are dependent, but there are no causal inference in between. Instead, there are latent common causes. Okay? So you can really verify all those things, discover causality just from data. I just gave a couple of examples. Okay, now, let me see how much time. So how much time do you think we can still? Okay.
Question and then.
Okay, maybe we can. I will stop very soon,
Yes.
because the last part can be merged to the next one. Okay, so now, tomorrow lecture, I will just merge some of them to tomorrow lecture. So here you can see in this example we have latent variable, right? So if you apply PC, you have no idea how to represent this result because you cannot use undirect link or this link or this link. So here, actually, we have to use a new representation produced by FCI. So with FCI right here, let me just say a few words about FCI. FCI is a causal discovery method that can deal with the latent confounders and also selection bias. Okay, basically it's very flexible, and then under facing this assumption, then this method, the result by FCI is asymptotically correct. Okay, however, to represent the outcome of this result of this method, we cannot use the previous pattern. We have to use another thing. We cannot use the pattern anymore. We have to use new types of edges, known as PAGs. This is partial ancestral graphs. There are a lot. Once again, there are a lot of terminology, but don't be scared. Now, instead of 3 different edges, now we have 5. We have a circle right here. Right now, we make use of weaker assumptions because we allow latent components. We allow everything. And then we have to make the representation more flexible. Circle means I don't know. Circle means, yes, it can go this way or it can go this way. In other words, if I have circle here, I know x2 is not a set of xy because I have an arrowhead here. Okay? This is just a circle. Now you can see we have 5. And this one, we have a latent common cause. This one, xy, the cause x2. Okay? That's it. Now, if you apply FCI to your data, you have a PAG with those 5 types of edge representations. Okay? That's it. You know how to interpret it. That's good enough. I didn't really talk about FCI, but you can see with FCI, we allow latent confounders. You can still get informative results. However, very often time you can see circles. If you see circles, basically it means I don't know, right? Circle could be arrowhead or arrow tail with I don't know. Later, tomorrow, you are going to see that by making use of some weaker assumptions, we can determine causal direction without any indeterminacy. Okay? You can determine the full deck from data by making assumptions. Right here, today, we only make use of conditional independent relations. It's very weak. Now, to complete this part, let me say a few words about the score-based method because usually we just talk about the constraint-based method and the score-based method at the same time. Okay? Previously, we only make use of conditional independent constraints. We try to find a set of decks or set of packs to satisfy the constraints. Now, let's use a different perspective. I try to find a score, and then I want to find a deck or set of deck to maximize the score. That's it. First of all, suppose this is true. And if you add new link, it's not necessary, right? Then we know that according to model selection criterion, like BIC, Bayes information criterion, this one would not be optimal. Okay. Similarly, if I have one fewer link, then this is not optimal because some dependent pattern cannot be explained by this representation. Okay. It's not optimal. Good. So with score-based method, we just try to find which is graph can give the best score. That's it. And this is the basic assumptions underlying GS greedy equivalent search published in 2002. I will skip the details, but basically, first of all, this assumption says all decks in the equivalent class give the same score. That's true. And the second one says if you remove some fake independence or fake dependence, then the score should be better. It's locally consistent. The last one says the score can be decomposed this way. If you use the BRC score, basically, BRC score is a likelihood function together with the number of edges, the penalization term, depending on how many links you have. Then this is decomposable. Okay, that's it. Then you can derive the GES procedure. There are two steps. First one is the forward step. The second one is the backward step. In the forward step, you just keep 80 edges to improve the score. And then at some point, you have to stop because no further link can improve the score. You stop. And then you try to remove links. That's it. So here, suppose this is a true graph. I first want to add one link to improve the score as much as possible. I may add this one if the coefficient is very high. And then I add second one. Now you can see I stop. And then try to remove links. I cannot remove any. This is the final result. Okay. Now comes this one. This is the last example. So suppose I have 6 variables, as you can see from here. Suppose all coefficients are 0.4. Then it's not surprising that X and Y will have very high correlation because there are 4 ways for them to be related. Okay, suppose that's the case. Now, if you use GS, which link would you like to add in the first place? Which link, which edge would you like to add? You start with an empty graph, no link. Now you want to add one to improve the score as much as possible. Then you add second one, third one, and so on until you have to stop because no further link can improve the score, right? So which one would you like to add first?
All are equal. Anyone.
Anyone? You want to improve the score as much as possible. Suppose, sorry?
Equal. All are equal.
Sorry? No, now it's empty. Now it's empty. We start with empty graph.
Yeah.
No link, as you can see from here. Yeah, yeah. Yes. Yes, you want to add the first link to improve the likelihood as much as possible. As I explained, suppose all coefficients are 0.4, then the correlation between X and Y will be very high. Then it's not surprising for you to add the link between X and Y because this pair of variables is very dependent. Adding a link to explain the dependence can explain a lot of dependence. As a consequence, the likelihood function can be much better. Is that right? So you first add this link, and then add the second one, third one, fourth one, and so on. And after that, you have to remove the first one. That's why the second step, the backward step, deleting step is also necessary. Right? After that, you stop. And it's guaranteed to convert it to the truth asymptotically.
Thank you so much. Thank you so much.
Okay, I'll stop here and So next time you see modern step method and together with how to detect latent variables. Thank you, please.
Thank you so much, Dr. Kun. So I think we have no time for question, but let's take one question. I have one question, but if someone else, please.
Okay, so for this, like I have a question, like I've seen the entire algorithm. For me, this was the very first time in my life I'm seeing this. So the way I see it, it's very much similar to the Bayes' theorem, which is basically we implement this in AI with the algorithm called as naive Bayes. I see it in a very similar fashion to a naive Bayes. Can you elaborate a bit, like how much is this algorithm adding on in terms of computational efficiency? Because you're adding another layer of interdependencies in a vertical manner for connecting the two nodes to it. That's the one part of it. Second part, don't you think like we are adding another layer of interdependencies, and if the data gets more, then it's more trivial to drive if we have two paths with the same optimal probability of occurrence, then it will be a trivial to choose which path to follow. then we will be needing another algorithm in order to optimize the path of the best interdependencies.
Which one? The similar, sorry, I didn't hear.
Okay, the first is the similarity between the naive Bayes and this algorithm, like in terms of computation efficiency.
Sorry. Oh, naive Bayes. Okay, naive Bayes. Naive Bayes is okay. What's naive Bayes? Naive Bayes is a method for what? Yes. So naive Bayes is basically a way for you to do classification. You have y, you assume given y, xi, the condition independent. But basically, they share the similarity because both of them rely on the definition of the concept of conditional independence. And naive Bayes does not tell you anything about how to discover the structure and whether you can recover, whether you can verify the conditional independence. Not at all, right? It's just assumption you can make use of for classification. Is that right? Okay. And second of all, the first one is did you talk about this method GES? Because you were commenting on the procedure, search procedure, right? Were you referring to GES? Yeah. Yes. No, sorry, you mean another layer of searching for the best.
The best path, what is connecting the two variables.
Yes. So you want to see whether two variables should be adjacent.
Right now, there are only two variables which are connected. But if I see it, I apply this algorithm like every fourth day of my life to keep my spread.
Yeah.
Right. But when you talk about the data at a scaling level,
Yeah.
then there is another problem which is being started with this algorithm.
Yes.
To find the optimal path for the two neurons.
Oh, you are saying right now we consider only pairwise relationships.
Yeah, yeah.
However, causality is about the pairwise relation. Why? Because if you fix other variables, then essentially it's just the two variables. And actually, that's a very interesting question. You go to a high level. There's whether I can consider three variables at the same time, right? So the answer would be it's not necessary in this case. Why? Because we assume faithfulness. If you assume faithfulness, then they are equivalent. But there exists one situation. Let me give one example. You have three variables, x, y, z. And then x, y independent. So you have three coins, right? Pair coins. X, y independent, 0, 1. And suppose z is determined by x, y. In this way, if x, y are the same, z is 1. If x, y are different, z is 0. Can you see it?
Yeah.
So x, y, z, they are independent binary variables. And in this case, you can see although z is determined by x, y, the independent from x, z is independent from y. So in this case, it's a violation of faithfulness. Then with this method, you cannot get the right answer. But if you consider combination of variables, the x, y together, then you may be able to find the right answer. So to summarize, it's possible for you to make use of multiple variables at the same time to derive a better method if faithfulness is violated. But if faithfulness assumption holds true, then they are equivalent. However, if you consider multiple variables in a combination, the complexity would be horrible because, it's a combinatorial problem. Is that answer to your question?
Yeah.
Okay. Thank you.
Thank you. Thank you very much, Professor.
Okay, thank you.
Very kind.
Thank you. Thank you.
And I know you were not feeling well, and despite that, you have so much energy. May you always stay like that. Thank you very much indeed. And tomorrow we'll continue. I'm sure a lot of people have a lot of questions with you. Thank you very much.
Thank
sir.
you. Thank you,
Thank you very
everyone.
much for the wonderful talk.